Alright guys, so let's get started. So today we're going to do the heat transfer mode. So this is extremely important. Extremely important. It's more important for the people that are aerospace because on your curriculum, you have a very good curriculum, but I think you are missing two classes, which is one called heat transfer and another one vibrations. Okay? So this is really the only exposure you're going to have to heat transfer unless you go and do a master at for the aerospace, with the aerospace department. So this is called heat transfer modes. Okay, so here we just touch the surface, obviously because there's a whole class about this. Actually, the whole class is more about just two of them than three of them, but anyway, so we kind of talk about this the first day of class when I introduced the material cover, and we said the different forms of heat transfer that are familiar are what? Conduction, convection, and radiation. And we try to give examples. So let's do that. So the first one is going to be conduction. So let's say the three transfer modes are conduction, convection, and radiation. And this is something that I think is important. I'll probably mention it, I'm not sure, but is that let's try, instead of thinking more about conduction, convection, and radiation, try to think more about the different mediums, okay? So let's start maybe by the most, probably the most difficult, let's say. What type of heat transfer do you have in space? So what type of medium do you have in space? You have vacuum, no? So there's no medium, really. So what do you have? You already say is radiation. So can we maybe relate the radiation to vacuum? So VACCUM. So this one will be the vacuum medium or media. Now, what about the convection? In what type of medium or media would you find that one? It should be air, no? So it should be like a moving media, no? The moving mediums will be moving media or medium. Really should be medium. It will just look at one fluid, but if we look at multiple fluids, it should be media. And now, so we already look at the vacuum. So this would be like liquids, if you want, / air, should be the classic examples. Okay, this should be space. Now, what about conduction? What is the only medium we haven't defined yet? The solid medium, no? So any type of material, let's say whatever, brick, any other thing, okay? Steel, aluminum, and so on and so on. So really, I think, it's more defined, it's more related to the medium about which one is going to be more dominant, no? Which one is really the most important. But obviously, in every single case, you have a little combination of the three of them. All right? Okay, so let's start by the easiest one, and actually you could spend a whole class just studying conduction. So let's look at the first one. Conduction. And we already know that conduction should be related to a solid media. Right? So the typical example here, let's say you have some type of wall or brick. So let's say think about the wall of a house. Okay, so let's say this is the wall. let's say this is the inside, outside. Okay, so in this case we are in Florida, so the outside should be hotter than the inside, no? Okay, in this case. So just like pressure, if you think about pressure or heat, but think about pressure. Does pressure move from high pressure to low pressure or from low pressure to high pressure? High to low, okay? So if you think about pressure and temperature are kind of related. If you have a bottle and you heat it up, what's going to happen to the pressure inside is going to increase, no? If you cool it down, the pressure is going to go down. So you could say that whatever behavior the pressure has, the temperature is going to follow the same one. So let's say the temperature is going to move from hot to cold, okay? So in this case, if this is the wall, the heat is going to try to go, the heat transfer. So here, be careful, it's Q dot. So Q dot basically means dQ in function of time goes from hot to cold. So let me say maybe this is hot. And this is cold. Okay, so heat transfer moves from hot to cold. Okay, and it's related to a solid. All right? So the expression for the conduction is given by, and I will do more figures here, is given by Q dot, which is dQ dt. So this is heat transfer in function of time will be equal to, leave some space here, leave a little bit of space here, Ka dt dx. Okay, so K is related to the material and is known as the, it's not rocket science, conduction coefficient, and this one is related to the material. Okay, so now A, here be careful, A is exposed surface. So if this is the wall, over here, so imagine it's easier maybe to look at the wall of your house. So what would be the exposed area? What is the exposed area of the wall of your house, let's say to the sun? It's all the outside surface of the wall in your house, no? Be careful, because here sometimes the mistake you do is that you think is the cross-sectional area of the brick of your house. No, it's the outside surface, correct? It's not the cross-sectional surface. So this is outside surface. So if we needed to do a plot over here, would be all this area over here. Okay, or here if you want, no? But it's the exposed area. So now, if I do a plot of the temperature, okay, maybe, yeah, let's put it this way. So this is your wall over here. I'm just doing it now. 1D. So this is the outside. This is the inside. And if you want, yes, we can do this if you want. Doesn't matter. I mean, it's just going to add more stuff, but so this would be T with the position X. Okay, so if the temperature is hot outside, let's say we have a temperature here, T hot. Okay? On this side of the wall, on the outside, you're going to have a T hot temperature. Now, on the inside, you want it to be cooler, so let's say you're going to have a T cold temperature. So, if we assume a linear variation of the heat, you agree that this will be the variation of the temperature throughout the thickness of the wall, no? Okay? And what will be the thickness of the wall? So let's say this will be X. So let's say this is X. And this will be what? Wall. In this case, so it will be just, yeah, wall thickness if you want. Okay, so here, maybe this is not that important, but at least to give the proper equation. All right, so this line over here has a positive or negative slope? Negative slope. What will be the equation of this line? Will be, if you do is change in height divided by change in length, no? So what will be? Tc minus Th divided by X. Correct? And this would be negative. So basically this is the equation of what we wrote over here, dt dx, no? Change in temperature, dt dx. So the dt dx, let me write over here, dt dx is what is known as the temperature gradient is negative. But we know that the heat going from hot to cold is positive. Yeah? So what do we need to do? We need to put a negative value over here. Okay, for the equation to be correct with the sign convention, no? Because this is negative, negative, negative will give positive. But again, personally, what I do most of the times is what? Forget about the sign, okay? This would be what? If you go from hot to cold, and if you do the slope, instead of doing Tc minus Th, you do what? Th minus Tc divided by dx would be positive, no? So now you can leave this equation as positive. Okay, but again, this is the real definition. Okay. So let's see now what is K. K is the conduction coefficient. So I'm going to pause the video for a second because I'm going to go online and find different values and then I restart the video. All right, so let's think about now conduction coefficient, which is K over here. You see the unit should be watts meter Kelvin. Okay, maybe I should add that now to the notes. And they give you this at different temperature, but let's look at solids, okay? What is the aluminum brass 121? If you think about it, if an object is a good electrical conductor, it's probably going to be a good thermal conductor, no? Okay, so let's look at brass. Probably would be good as well. Do they have it brass here? No, brass, oh, brass is low. So copper, let's look at copper. Copper, I didn't know brass was bad conduction. Oh, that's probably why it has bad, is good for oxidation, doesn't. So copper should be very high. They don't give the value. Okay, let's see if it gives here. Anyway, conductor, if they conduct electricity, it should be high. If they don't conduct electricity, the value should be a little bit lower, all right? So here you see aluminum is pretty high. Now let's move more to copper here was given is 413. Okay, it's even higher. Now let's say about, I saw before, balsa wood. Do you think wood is a good conductor? Probably not, no? Balsa wood should be a small value, so that should be a good value for insulation. All right? Let's look at other values. Brick, 0.15. Okay, so basically what's important to notice that the K value is related to the material. So you can find tables with different values of K you see for different temperatures. Let's look maybe at one more material. So let's see glass. Is glass a good insulator? So you see it's not good conducting electricity, no? Glass. So you should have a low thermal conductivity, all right? So here what's important to realize is that whatever the material is this wall made of, you cannot really stop the heat transfer. But what can you do? You can slow it down, okay? So in the optimal condition, you can maybe slow it down until, if it's during the day and it's hot, until it gets dark. So now it's gonna cool down outside, no? Okay, but you cannot really stop it. So let's look at the units. So basically we have the units for the heat transfer. So Q units. Q is in watts. Obviously, A, which is the area, should be in meters square. All right, dt dx should be in what? Kelvin per meter, no? So K would be, what would be the units of K? Units of K should be proportional to what? Q dot divided by A dt dx, no? Which is what? Watts, meters squared, Kelvin over meters. So units of K should be watts divided by meter Kelvin, which is what we had on the tables that I show online. All right. Let's go and do 248 as an example. All right, so I'll try to put on the screen as I do it, because like I mentioned, I think it's important that you learn how to solve the problems more than sometimes the material. And if you take different classes with me, it's always the same process. Okay, I don't change doesn't go different classes, doesn't go with a different process. So I hope you can read. Yeah, so as shown in figure 248, an oven wall consists of a 0.635 thick layer of steel. So let's see what that figure is. All right, so this is the figure. Let's do the figure and then I'll go put the data. All right, so it's steel and brick. So let's do the figure of brick here. Then we're gonna have brick. So let's see what do we know. We know the thickness of the brick. No, L steel, sorry, so L, let's say this is L steel is 0.635 centimeters. This is the thickness of the brick, LB. The temperature outside the brick, so here temperature is 40 degrees Celsius, so let's call this one T infinity, so it will be the area of the surrounding of the air and the area inside the oven. So here is one should be T let's say steel is 300 degrees Celsius. And it looks like the temperature gradient between the inside and the outside of the steel is, so delta T is negative 0.7 Celsius. So I don't know which one I'm going to use, but this will mean what? That the temperature inside, so let's say here T sub I inside the steel should be equal to what? To 99.3, no? Okay. Then from the previous page, we had a bunch of information about the brick and the steel. I think you see the thermal coefficient. So, I mean, I can do it symbolically. I'm not that concerned about the values. K steel, the theta is equal to 15.1 watt meter Kelvin, and that the brick obviously should be smaller, no? It's a better insulator. 0.72 watt meter Kelvin. At steady state, the temperature decrease of 0.7 occurs over the steel. The inner temperature of the steel layer is this 300. If the temperature of, that's what we need to solve, on the other surface of the brick must be no greater than 40, determine the thickness of brick. So I guess LB in centimeters. Okay, that ensure this limit is not met. What is the rate of conduction in kilowatts per meter square of wall surface? Okay, so basically what we need to do is solve for L sub B and Q dot over A question mark, which is what, and the answer in kilowatt per meter square. So kilowatt per meter square. So guys, something that I always say, okay? I don't come with a solution or nothing. So to me, I need to do the figure, I need to read the problem, and I need to put all the information that I know on a piece of paper, okay? To write it down. This is not a waste of time. It should give you time to fully understand the problem and gives you time to think about the problem, okay? That's what I'm doing now, okay? All right, so here, as we said before, what do we know about the heat? We know the heat is going to go from hot to cold, no? Q dot, all right? So what type of heat transfer mode we're going to have? Conduction, all right? So we can say Q dot, and be careful here because this is generally a mistake that you do. And the total amount of heat transfer Q over here. So this is my question. The total amount of heat transfer going through the steel and the brick, is it equal to the heat transfer going through the steel plus the heat transfer going through the brick? Let's say option A, okay? Option B is the heat transfer going through the steel equal to the amount of heat transfer going through the brick? Which one do you think it is? Think out in your head. A or B? Now we'll see what it is, okay? So the answer is on the figure. This is like an electrical current. If you have a cable with one resistance and another resistance, what is the amount of amperes, okay, or current that goes between both resistance? Is it the resistance that goes through one plus the resistance that goes through two? No, it's the same one, no? Okay, so here's the same thing. Remember, Q is the heat coming from the outside. All right, let's say you have your house, the first layer will be bricks. all the heat is going to try to go through the bricks. Land you might have, on the next leg you probably have some type of insulation material. All the heat is going to try to go through the insulation material. Okay? So the amount of heat is the same going through the whole wall. Okay? So that's the important part. So let's say, what would be the Q going through the steel? Would be negative K steel. Now, that's probably why they give us this. It will be this change in temperature, no? The temperature gradient over here between 300 and 299. You will have that line over here. Okay, but let's put the general here will be dt dx. This is the general expression. In our case, what should be this dt dx? Should be delta T over L sub S, no? Yeah? Okay? So this would be the amount of heat going through the steel. And I forgot here the A. But I mean, you can put it at the end if you want. Put it over here. A. Okay? Now, the amount of heat going through the brick will be equal to what? Minus K brick A, same expression, dt dx, but now the dt dx would be, let's say this is the dt dx would be the one going through this line. All right? So obviously, what would that be? So this dt dx here should be equal to what? T, if we use a negative value, should be the T infinity minus the T inside, correct? This one minus the one inside divided by what? The thickness of the wall, which is L sub B. And what did we just say? The amount of, and this is the most important equation, really. What is the amount of heat going through the steel and the brick? It is the same. Okay, so you can say the general heat Q steel will be equal to Q brick, which will give you, so this is the equation that I would like to see if this problem is in an exam. I'll be looking for this equation because this is the one that shows me you understand the problem. And now you can just rewrite minus KSA delta T LS equal to minus KB A T infinity minus T initial over L sub B. So basically, we are almost done with this problem. We just need to solve this equation. So you can see, you can cancel the A, you can cancel the minus sign if you want. Do we know Ks? Ks is known. Kb is known. Delta T is known, is negative 0.7, and Ls is known, is 0.635. T infinity is known, 40. T inside is known, 299.3. We need to solve for LB. Okay, the unknown here is LB. So let's just simplify that equation first. So this will give us Ks delta T over Ls equal to Kb T infinity minus T initial over LB. So this will give us what? LB should be equal to Ks over K brick. No, KB. No, LB will be KB, sorry, KB over K sub S. Then we'll have T infinity minus T initial divided by the delta T times L sub S. Okay, in this problem, we know that K sub B is given to us is equal to 0.72. K sub S is equal to 15.1. And then T infinity is 40. T inside is 299.3. Delta T is negative 0.7, and L still is 0.635. Okay, so if we do the numerical application here, guys, just be careful a bit. I mean, in this case, very simple, but it's not a good thing. Here they ask us to do the problem in centimeters, and really the case is given in watts in meters, no? But do we need to change the units? No, because it will cancel, the top one will cancel with this one. And the same thing for the temperatures. Okay? So we don't really need to change the unit. So you could do over here what? 0.72 divided by 15.1. Then we don't need to change the temperatures either because it will cancel, and it doesn't matter if you do the difference between two temperatures, it doesn't matter if you do it in Kelvin or Celsius, no? So this will be T infinity minus the T inside, so this gives you 40 minus 299.3 divided by negative 0.7, and then this will be so unitless, and then you have here 0.635 in centimeters. So this is the units you will have, centimeters. So if you do this calculation, what do you get? Okay, so once you do a calculation, you get approximately 11.22 centimeters. So that means that the minimum thickness of the brick wall of the oven needs to be about 11.22 centimeters if you want to make sure that the temperature outside the wall is at least 40 degrees Celsius. Okay? So then the second part is to find Q over A. Now we say that the Q, the total Q, is the same, should be the same Q going through the steel as it should be the same Q to go through the brick. So we could calculate the amount of heat transfer per unit area from either this equation or this equation, no? So let's go ahead and check. We should get basically the same or extremely close to each other, depending on the approximation you did for the L sub B. All right, so to find Q over A, we know that Q sub steel will be equal to the Q sub brick, and let's say this will be the general Q. So we know Q could be equal to either K sub brick, so minus K sub brick A, this was T infinity minus T initial over LB, or this could be equal to minus KS steel A delta T over L steel. We need to find Q over A per unit area in kilowatts. I can just divide by A, everything. And this will give us minus KB T infinity minus T initial divided by LB, or minus KS delta T divided by LS. So let's go and check. Let's say Q over A first will be equal to minus KB T infinity minus T initial over LB. You do the calculation, you give me the value, and then you redo the same calculation now by doing Q dot over A will be equal to negative KS delta T over LS. Okay, and let me know what you get. Okay, so some of you did the calculation, and basically you see that the result is very close, 16.65, 16.63. I think this is watts, so if it was kilowatts, you need to divide by 1,000, no? So it should be 0.016 kilowatts per meter square. And basically the difference probably comes from the round-off that you did for L sub B. Okay? If you take more decimals, it will probably get, I mean, it should be identical, no? If you take all the decimals. All right, so remember one thing important about the heat transfer is that the heat transfer going through multiple surfaces is the same. It's not the summation of both of them, no? Okay? Think about electric power. The intensity going through multiple resistances is the same. Okay? This is the same concept. All right. So we are done with this problem. So now let's move to the second case, which is convection. Okay, so convection. I give you the equation is heat transfer, Q dot, which is equal to dQ dt, it's the same thing, it's per unit time, is equal to HA, and let's over here say T hot minus T cold. Where again H is the convection coefficient, A is the exposed area, and then okay, TH minus TC, let's say this is delta T, which will be the temperature change. Okay, so over here, maybe to do some type of figure, imagine we have, think about a computer, we have a fan over here. That creates heat on what can I do here? Let's say on a microprocessor, all right? What would be the area? The area would be the outside surface of the object, no? Imagine there's a fan in this room and you're under, the exposed area will be your skin, no? Whatever is exposed to the air, all right? And now, the convection coefficient will be related to what? It will be related to the liquid or to the air, no? To the moving medium. Okay, so this is now very important to understand is that H is related to the medium, which can be air or liquid. And now, if it is air or liquid, have you seen this before? I mean, did you have a class in fluids before going to this class or no? No? Okay. But I mean, we can understand this part. Just do the figure. Maybe you don't need to understand it at this far, but let's say this is the value of the h, okay? Or the velocity, all right, of the flow. So this flow will also be related to the velocity of the flow. So the higher velocity you put on the fan, the higher should be the h, okay? The lower velocity you put on the fan, the lower should be the h, correct? So you see that the h is already influenced not only by the type of fluid that it is, air or gas, also by the velocity of the air or the gas, okay? Now, is the velocity going to be the same, let's say, if it is you on your skin, at the surface of the skin, than it is 10 centimeters from your skin? No, that's what is called the velocity profile. So when the air touches your skin is going to try, because of friction, try to stop the velocity to zero, no? And the more far away you move from the skin, the higher will be the velocity until you get to the velocity of the flow. So also the velocity will depend on the quality of your skin, maybe on the color of your skin or what the type of skin that you have. The h will be different, okay? So the h is a very difficult constant to find. Basically, you're not going to find it on the internet or on any table. You need to evaluate it, all right? There is some complicated expression to find the h for air. You probably will see that in heat transfer, but you're not taking heat transfer, okay? But maybe in aeroacoustics, when you do aeroacoustics for the design of engines, you will have to take values for h, okay? And there is some complicated equation for the air to determine. But h, this is a complicated to obtain. So it's not, you cannot find it on table. So in this class, it needs to be given to you, all right? Otherwise, there is some relations that can give you the value of h depending on the Reynolds number. Have you seen the Reynolds number to define the quality of the flow? If it's laminar or if it's not laminar. Anyway, you will see that in fluids, okay? Then you have other numbers, the Nusselt number and so on. So basically, the convection is very difficult because of the h, because the equation is very simple. Once they give you the h, the rest is very simple, no? Okay? But that's the only thing I want you to remember. Now, that h, convection, is really difficult because of the h, but in this class, it's going to be very simple because the h will be given to you. So what should be the units of h? So again, the heat transfer will be in watts. A would be in meters square, and the difference in temperature will be in Kelvin. So this will tell you that h should be Q dot divided by A delta T, so it should be watts, meter square, Kelvin for H, okay? Should be the unit. And same as before, let's go and let's do a problem. Okay, guys, so just because I just saw that the example has conduction and convection, let's cover first convection, radiation, sorry, and we'll do the problems that involves radiation and convection. So, radiation, 3. Radiation, this one was related to the vacuum medium. And basically, we're going to have here that Q dot is equal to sigma epsilon A T hot to the 4th minus T cold to the fourth. So now that one looks more complicated, but really it's not. So here the example is, imagine you have the sun, T hot, that is putting heat on whatever, on your car. Okay, so sigma over here is the Stefan Boltzmann constant. That value is on the page that I gave you, but let's go try to go and find it anyway. So over here you see sigma is the Stefan Boltzmann constant, and if you want to write down this down, is equal to 5.670374. That should be enough for us. 10 to the minus 8 watts divided by meter square Kelvin to the fourth, okay? Or you have here different units in BTUs will be 1.714 10 to the minus 9 BTUs hour foot square right hand to the fourth. All right. Okay. Now, epsilon over here. Okay. So you all know that. What is better to have for the heat? A white car or a black car? Are both these cars going to absorb the heat from the sun the same way? No, the black is going to absorb more heat than the white one, no? Okay, that's because the black is considered as a black body, so it's going to absorb more heat than light colors, all right? So that factor is taken into consideration by the epsilon, which is interesting because it's called the emissivity, but it could also be called the absorptivity, no? It's not how you absorb. It's because the real equation really should be Q being absorbed minus the Q gain emit, okay, for the emissivity. But since those values are so close to each other, somebody had to decide between one and the other, not to write down the equation. Okay, so they just decided to use the emissivity. So in this case, epsilon is the emissivity, okay? And let's say the emissivity will always be between 0 and 1. This would be what is known as the black body. And if it has to be 0, it will have to be what? Completely clear, no? All right. I think that's it. A, again, will be the exposed area. And I think that's it. Okay. So basically we have the equation for the radiation is epsilon, so sigma epsilon, the area times the temperature to the fourth. All right, so let's go to the example. You know, I always try to pick the examples with figures. I don't like to read the problem statement. So let's do the 235. I move this one to the left. Yeah. Okay, so 235. Can you read it? Yeah. I move this stuff up. Okay. The outer surface of the grill. What did I do? The outer surface of the grill, as shown in the figure, I think it means is at 47 degrees Celsius. And the emissivity is 0.93. The heat transfer coefficient for convection between the hood and the surrounding is 27 degrees Celsius is 10 watts per meter square. Per Kelvin, determine the net rate of heat transfer between the grill, hood, and the surrounding by convection and radiation in kilowatts per meter square of surface. I mean, this is extremely easy, but obviously we need to do an example. So let's do the figure. So this is problem 255 on the 8th edition. All right, so let's do a picture of the grill. That's a Jari grill. Now they have the little arrow. It's not a robot, okay? Okay, so what do we know? From the figure, we know that the temperature of the surface of the grill over here, that they put over here, all right, looks like they say T sub C, I guess, 47 degrees Celsius, and that the emissivity is 0.93. So here we're going to have to be careful with the units. Then what do we know? The temperature of the surrounding over here of the air, T sub naught, is 27 degrees Celsius, and that the conduction coefficient H is 10. Watt per meter square is Kelvin. I don't have space, so I'm not going to put it. And basically they ask you what is the total heat transfer. So how much heat is this grill going to lose? Okay, it's losing. We need to find Q total, and I think they say per unit per meter square. Okay. So over here, we have to deal with two different heat transfer modes, convection and radiation. So in this case, it's going to be is different. So the total heat transfer mode will be equal to what? All the heat that you lose by convection plus all the heat that you lose by radiation. Okay? So now, all we need to do is know the equation. So what is the equation for convection? It's H, convection coefficient, which is given to us. The area, outside area of the grill, that is A. Okay, the exposed area. And now is what? Is the difference between the temperature of the surface of the grill and the flow. Okay? And we go from hot to cold. So what is the temperature of the surface of the grill? T sub C. What is the temperature of the floor? T sub naught. Okay? So that's it. This is for the convection. Now, what do we know about the radiation? It should be equal to the Stefan Boltzmann constant, sigma times epsilon, the emissivity of the grill that they say is 0.93, so probably it's painted in black. Why do you want the barbecue to be in black? Because maybe it's going to absorb more heat from the sun and it's not going to lose heat that fast, no? Due to radiation. Okay? All right. So the other one now should be the temperature. So, okay, A here, the area. And that should be the temperature of what for the radiation? Should be the temperature. What are we going to have now? Okay, so should be the hot should be the Tc to the fourth, and this is going now to the medium, which is T0 to the fourth. Okay, so over here, really, what do we need to find at the end? We need to find the heat per unit area. So we can do Q total divided by A, because the area exposed to convection and radiation is the same, will be equal to H Tc minus T0 plus sigma epsilon Tc to the fourth minus T0 to the fourth. Okay, so now for the numerical application, I want you to be careful, because in this case here, can you keep the temperature in Celsius? For this term, yes, because the difference of temperature in Celsius or not will be the same, no? But can you do the same thing here? No, so you need to have them here, yes or yes in Kelvin. So I would suggest to move everything to Kelvin and do every calculation with Kelvin, no? Okay? So let's see, what do we know? So for the calculations, we know that T contact is 47 degrees Celsius, so that will be 273 plus 47 will give you what? So it will be 280, 320? 320 Kelvin. Then we know that T naught is 27 degrees Celsius, so this will give us 273 plus 27 will be 300 Kelvin. The emissivity is 0.93, and the Stefan-Boltzmann constant we just say was equal to 5.670374. 10 to the minus 8 watts, so that's correct. Meter squared, Kelvin to the fourth. So the units should be okay, no? All right, I'll put all here the units. So go ahead and do the calculation for me. And we should get here Q total over A. So depending on the units, we're going to use kilowatts or watts. What did they ask in the problem? Kilowatts or watts? Let's see. In the problem, they ask us per kilowatt. So give me the result per kilowatt. Okay, so I think we got about either 0.325 or 0.326 kilowatts meter square.